Have you ever just, stopped and wondered what everything is really made of? I mean, not just atoms, but the absolute fundamental, indivisible bits that make up you, me, the stars, the whole shebang? Well, believe it or not, physics actually has a map for that. And in this explainer, we're going to use it to take a tour of the very building blocks of reality itself.
It's maybe the biggest question you can even ask. And for the past 50 years or so, our best answer has been a theory so successful, so powerful, that it's just called the Standard Model. Think of it as an inventory of all the fundamental stuff, and crucially, the rulebook for how all that stuff gets to interact.
So here's the key idea. We're talking about elementary particles. These things aren't just small, they're the end of the line. You can't slice them in half, you can't break them down any further. They are the final, tiniest Lego bricks at the very bottom of the cosmic toy box.
Okay, so to make sense of this whole particle zoo, physicists have grouped all of them into two main families. It's a really simple, elegant idea. Just think of it as the bricks that actually build all the matter, and the glue, the forces that holds all those bricks together.
And here it is. This is the Standard Model chart, our map to that subatomic world. Now, I know it might look a little intimidating at first glance, but it's actually brilliantly organized. Over on the left, you've got the matter particles, the bricks. And over on the right, you've got the force particles, the glue. Let's break it all down.
Right, so those two families have official names. The matter particles are called fermions, the force-carrying particles are called bosons, and that's it. Fermions are the stuff, bosons are how the stuff interacts. Honestly, this is the most important organizing principle of our entire universe: stuff and rules.
All right, let's start with the fermions, the particles that actually have mass and make up everything we can see and touch. If the universe is one gigantic structure, these are the bricks, the steel beams, and the foundations it's all built from.
Now, it turns out, even this matter family is split into two distinct groups. You've got the quarks, which are kind of the social butterflies of the particle world, and then you've got the leptons, which are a little more independent, let's say. Quarks are fascinating because you can never, ever find one all by itself. Seriously, they are always found clumped together in groups, forming bigger composite particles. They're the ultimate team players. They literally can't exist alone.
So how do they team up? Well, these particles built from quarks are called hadrons. If you stick two quarks together, well, technically a quark and an antiquark, you get a meson. And if you stick three quarks together, you get something called a baryon.
And this is where it gets really cool. You've definitely heard of protons and neutrons, right? They're packed into the center of every single atom. Well, guess what? They're baryons. A proton is just two up quarks and one down quark. A neutron is one up and two downs. That's it. That's the recipe for the heart of all matter. Amazing.
Okay, so what about that other group of matter particles? Those are the leptons, and the most famous lepton of them all is one you know very well, the electron. That tiny little particle that zips around the nucleus of every atom and literally powers our entire modern world.
So we've got our matter particles, the fermions, but they don't just float around randomly. Something has to tell them what to do. And that is the job of the bosons. They are the carriers of the fundamental forces of nature. They are the rulebook for the entire game.
First up is the heavyweight champion, the strong force. And the name really says it all. It is unbelievably powerful. But here's the catch. It only works over unimaginably tiny distances, about the size of an atom's nucleus. Its main job? To wrestle those protons and neutrons together and hold on for dear life.
And the boson that carries the strong force is just perfectly named. It's the gluon. It acts like a cosmic superglue that overcomes the fact that all those positively charged protons are trying to fly apart. It's what locks them tightly together inside the atom's core.
Next up is a force you experience every single second of your life: electromagnetism. This is what holds atoms and molecules together. It's responsible for light, for electricity, for magnetism, you name it. And unlike the strong force, its range is infinite. The carrier for the electromagnetic force is the photon. Yep, the exact same particle that makes up light. So next time you turn on a lamp, you're literally seeing countless force-carrying bosons streaming out and hitting your eyeballs. Kinda wild when you think about it.
The third force is called the weak force. And yeah, it's much weaker than the others and has an even shorter range, but it's absolutely crucial. Its main role is in radioactive decay. It's the force that allows a neutron to change into a proton. That's a process that helps power the sun, so kind of important.
And you guessed it,
The weak force has its own messengers too, the heavy W and Z bosons. They're the go-betweens that allow these vital particle transformations to happen.
Okay, so we've met the whole cast of characters, the matter particles and the force particles, the bricks and the glue. Let's put it all together now and take a look at the complete, beautiful picture that physicists have assembled.
And we're back to our map. But it should make a lot more sense now, right? You can see it all laid out. The matter particles, the fermions, on the left, and the force-carrying bosons on the right that tell them how to behave. It's a stunningly complete and just elegant picture of reality.
And here's the thing you have to understand. This isn't just some pretty chart. The Standard Model is one of the single most successful scientific theories of all time. Its predictions have been tested and confirmed to mind-boggling degrees of accuracy for decades. It just works.
But you might have noticed something missing. We've talked about the strong, weak, and electromagnetic forces. They're all there. But what about the force that's keeping your feet on the ground right now? Where is gravity?
And that, right there, is the biggest secret, the biggest omission in a Standard Model. It perfectly describes those three forces, but it has absolutely nothing to say about gravity. The math just doesn't fit, at least not yet. This means we know for a fact it's not a complete theory.
So this fantastically successful user's guide to the universe is missing one of the main characters. It tells us so much, but it also points directly to an even deeper mystery. The Standard Model is our best description of reality so far, but it's also a giant clue that the story is far from over. What do you think comes next?